models. And to be honest, Sylvia and Alex's talk sufficiently covers my talk, but I hope I can add something new. Well, today's talk is largely based on the paper Okazaki and Yoshimura published in 2019, a little bit old, but I haven't introduced it yet in this community, so I'd like to share this results. So first of all, I would like to introduce the motivation of the study. Well, okay. Well, I would like to reconstruct paleoclimate with data assimilation. And there are many studies assimilating proxy data to reconstruct paleoclimate. But in the many past studies, the proxy data is not directly assimilated. But first, the proxy data is once converted to temperature or some other variables that is easy to handle, and then assimilated. And at this point, this strategy works well. What I want to do is assimilate proxy data directly. The reason why I want to do this is that when converting proxy data to temperature, there must how can I say, noise must be included in the process, right? And in this conversion, the stationarity between proxy data and temperature is assumed. But as many of you already know, that's not the case. Sorry. So that's the reason why I want to assimilate proxy data directly. But in data assimilation, GCM simulation and model simulation and proxy data must be directly comparable. And GCM simulation in general does not have proxy data and proxy values. So GCM simulation must be converted to proxy data, and observation operator, or in this case, proxy system models, converts the model states to proxy states. So in data assimilation, if you want to do direct data assimilation of proxy data, the observation operator or the proxy system model is the important part. So we need to evaluate if observation operator is sufficiently skillful or not. And for that purpose, I think we need to do evaluation of observation operator. And if there is a isotopic observations at the sampling site of proxies, we can use that observation to run the observation operator or the proxy model, and then combine the simulated and compare the simulated results with the proxy data, and then we can evaluate if the observation operator is correct or not. But in reality, that's not the case. We do not have any. It's quite rare we have isotopic observation at proxy sampling site. So we need to create isotopic data first. For that, we need very nice isotopic information, atmospheric information. So I first developed our new isotope-enabled GCM, and then evaluated, and then confirmed that the model is sufficiently skillful, and then use that information as input of the observation operator and to run the observation operator, and then compared the simulated proxy data, and then compared it to the proxy data itself. That's how I will talk today. Okay, so first of all, I would like to introduce MIROC5-iso. So the implementation of stable water isotopes is generally the same as the other isotope-enabled models. But the MIROC5-iso has a cloud microphysics. So I implemented water isotopes to that scheme, and it was based on Rossi et al. 2010. And I implemented isotopes into the atmosphere and land surface component of the MIROC5, which is originally a couple of models that I only implemented isotopes into atmosphere and land surface components. And for the implementation into land surface component, I followed Yoshimura et al. 2006 named isotopic. And yeah, fractionation is fully considered in all the processes that rate phase change. So I first validated the atmospheric model itself, and horizontal resolution is T42. That is about 300 kilometers, and it was forced by observed SST, CI, greenhouse gases, etc. And wind fields are merged toward JRA25. That is a reanalysis. And the simulation period is 1979 to 2007. Okay, so this slide shows the isotope precipitation, isotopes in precipitation, and climatologies are shown of GNIP, swing to ensemble mean, and MIROC5. You can see that well-known feature of the isotope creation in precipitations, I mean, latitude effect and altitude effect here, and continental effect. So it's okay. And when the performance is compared with the other models, I would say the performance is not so different from the other. When you see the Taylor diagram here, the ensemble mean of the swing to models are plotted here, and MIROC5 is plotted here. So it should be okay, but nothing special. But and then I compared, I evaluated the internal variability of isotope creation in precipitation, as well as temperature field and precipitation field. So the average correlation is 0.262 for temperature, and 0.48 for precipitation, and 0.34 for isotopes in precipitation. So the scales are less compared to the other fields, but that is reasonable, I think, because the isotopes are affected by temperatures, precipitations, and many other variables. So the errors in such other variables must be accumulated. So I think the regulated scale is quite reasonable. And then I compared the scale for isotope creation in precipitation to the other models. Well, the table shows the number of sites where correlation between simulation and GNIP data is statistically significant for the regions of Northern Hemisphere, tropics, and Southern Hemisphere. At all the regions, MIROC5 performing well compared to the other models. But I don't want to say that MIROC5 is the best, and probably it was because of the nudging field I used was a good combination with MIROC5. So as Hyon Bon talked yesterday in his presentation, we should care about which field, I mean, which reanalysis field product should be used in the comparison. Well, anyway, MIROC5 and JR25 combination worked well for precipitation isotopes in precipitation. And that is true for synoptic scale variability. The figure shows the synoptic scale variability at Fuji, Antarctica. Actually, this slide is from Kanon Kino, and she will introduce this result in detail right after my talk. So I would like to skip this. And then how about vapor? That slide compares model and observation for delta D of calm integrated vapor. Left two panel shows the schematic and COSAT, and MIROC5 is shown in the middle. For the Northern Hemisphere, the seasonality is shown in the slide. So over the Northern Hemisphere, it's negative, and it's well simulated in the model too. But when it comes to the Southern Hemisphere, the signal is totally different. In observations, the difference is positive, but in the model, the difference is 0 or rather negative. And this tendency can be also seen in the other models. Actually, I have no explanation for this, and I'm very happy if you have any idea to explain that this discrepancy between model and observations. And because MIROC5 has one surface component, I can compare its isotope ratio in river flow with observations. So the two figures shows compares the observed isotope ratio in river flow and MIROC. And upper panel shows the mean, and it seems that the MIROC5 captures the spatial variability, and it should be because of the precipitation is well simulated. But when it comes to correlation, the reproducibility is not. Well, actually, the correlation is significant only at 13 points out of 121 points. And probably this is because the process, land surface process is not well simulated in the model. Well, the right two figures compared observation and simulation for soil moisture. Blue is, line is simulated one and dots are observation. And depth is not the same, so we cannot compare directly, but the discrepancy is apparent, especially for B site. And well, the observation site is not enough to conclude what's the problem. But so I think we need more observation data for moisture. And at this point, I highly doubt the land surface process is problematic. Okay, so how much time do I have?
3-4 minutes.
Okay. So from here, I'd like to evaluate proxy system models. So there are lots of proxy system models now. For example, for miniatura, developed by Schmidt et al. 1990, ice cores, corals, dream solos, and skeletons. And I believe there should be more. And Sylvia developed a very nice tool, set of such proxy system models named Prism. But today's talk, I would like to evaluate ice cores, only ice cores, corals, and dream solos. That choice is arbitrarily made. So simulation settings. For ice cores, I used these model that considers only diffusion in the snow. And the corals, for corals, I use Wheelband's model, and which combines SST and ocean isotopes linearly to produce isotopes in corals. And for string solos, I use Lorentz model, Lorentz classic model. And as Alex explained in the previous presentation, the monthly value is weighted by mean primary production to provide annual mean data. And atmospheric GCM to drive the PSMs are generally the same as the previous simulation, but that is forced. Wind fields are nudged toward NSFM Calgary analysis 1 or 20th century analysis, and the simulation period is 1950 to 2007. So the figure shows the correlation for each proxy types. Left three panels are for ice cores, and right top is for coral, right bottom is for twin solos. The color shows the correlation, and mark shows if the correlation is significant or not. So generally, it seems okay. I mean, maybe at many sites, simulation and observations are correlated each other very good. But when you count the number of the sites that is significantly correlating, the result looks differently. So the table just counted the raw numbers, and the figure shows the ratio of sites where correlations are significant. And for ice cores, corals, dream solos, and isotope ratio and precipitation. So for corals and dreams, the scales are almost same as precipitation, so which is good. So probably for those models, we can use them I mean, we can trust those proxy system models. But for I-scores, the skills are relatively slow. And but it does not mean that proxy system itself is bad. I mean, I didn't explain, but the color shows the atmospheric data to try proxy system models. Blue is MIROC5 nudge toward and program analysis, and orange is MIROC5 nudge toward 20th century analysis, and gray is isotopic nudge toward 20th century analysis. So you can see that when the proxy system model is nudged, driven by atmospheric simulation nudged toward 20th century analysis, the skill becomes worse. And as you can imagine easily, many I-scores are in Antarctica, and 20th century analysis performance is bad in Antarctica, so which explain this gap. So it's very difficult to evaluate proxy system models because its performance is largely affected by the performance itself, performance of atmospheric simulation that is used to drive proxy system models. So I cannot say any I cannot draw any conclusions here, but at least I think correlatory is good enough. For I-scores, I think I need more observations proxy sampling site. So let me finalize my presentation by showing our MIROC5-iso group's future plan. So we are going to develop MIROC6 and 7 isotope version that is a successive of MIROC5-iso, and the group is led by K. And for several years, I and K are the only members of this, but now we have Alex, Kanon Kino, and Satoru Shoji. So I think we can accelerate our study. And we are very interested in doing paleoclimate data simulation, also participating in Swing 3. So I'm very happy to cooperate all of you. Thank you very much.